Hello ladies and gentlemen, welcome back to Lecture 12 for GGS 300 Quantitative Methods for Spatial Science. Today we're going to be focusing on inferential spatial statistics. So well done on those of you who have now completed the midterm. Most of you I think have completed this, so good job on getting that revision done and really getting those grades high. It's really going to set you up for a good performance on this class overall. Today I'm going to be setting the next assignment, which essentially will be due a week from the day that it's set, so November 18th. Do let me know if you've got any queries or questions about any of that content, but hopefully it should be fairly straightforward to you. Okay, so we'll go over that, the work that will be set in the second part of this lecture as to how you're going to do that exactly, and that's going to involve a little bit of ArcMap. So it's going to be a little bit lighter on the level of R that you're going to need to use this week. So just so you know where we're at, essentially we're going to be finishing up the class after we've completed these next 3 lectures, okay? So that's good for you because then you'll be able to have a bit of a breather after you've finished the semester. So today we're going to be going over the spatial statistics part, and then we're going to be basically wrapping up by focusing just on correlation and then on regression. Okay, so these are the 2 kind of core parts of the course that we've been building up to over the past 12 weeks or so. So this is really kind of the penultimate few sessions before we finish, and these are really important tools that you're going to learn, particularly as we get into learning regression techniques. Okay. Then obviously at the end we have the final exam, so hopefully you'll have performed well on the midterm, you'll have got all of your past classwork back now marked, and then that basically sets you up for working out how you need to perform in the final 3 weeks in order to really kind of ace the module and come out on top, okay? So today let's get straight into inferential spatial statistics, and you know this by now that we've started to move over onto these kind of more formalized hypothesis testing approaches. Obviously we've done that in a kind of aspatial way, so it hasn't been focusing on any type of spatial quantitative methods for evaluating these hypotheses, but whereas we can do that with the type of more formalized approaches which I'm going to teach you today. So in those previous descriptive examples we focused on things like central tendency or dispersion of the distribution, but today we're going to be kind of looking at whether we get spatial patterns occurring, maybe just at random, or whether we can test them in the same statistical way that we have done in the previous classes to say that the pattern that we have obtained is significantly different from just a random pattern that might occur. And this is really kind of a handy set of techniques that allows us then to analyze everything from the way that cities work through to any type of other geographical application that you might be interested in. Okay, so looking at ecosystem developments in national parks, whatever your flavor of kind of spatial analysis is, this could be a really kind of useful set of techniques for you to understand. So essentially what we want to know is, are these patterns occurring at random, or is there something significantly different from just kind of what we would expect to occur? And what you would kind of expect to understand is whether they're either highly clustered, highly dispersed, or in the middle basically just random. Okay, so this is just a bit of an example for some points here. This would be a highly dispersed data set where the points are all really far away from each other. We could have kind of this random part in the middle here where they you have a few clustered and a few dispersed, and then over here you have a completely clustered data set where all of your points are close together. Okay, and you could look at this not just for points but also for polygons as well. So you can see here that we've got polygon boundaries, but those boundaries actually have some sort of categorical or gradient indicator within them. So over here we have quite dispersed patterns, whereas over here we have basically the opposite. So these are highly clustered, these types of outcomes that we have here. So the purple and the different shades of green, they're very, very similar to each other in the areas where they're coloured like that, so the neighbours are more likely to be their same colour. And this isn't just kind of something that occurs, theoretically. This is something that we often have occurring as an outcome of some sort of process that we've carried out. Okay, so I'm going to use here examples for presidential elections. So here is the 2008 presidential election outcome. for either Democrats or Republicans, so obviously blue and red respectively. And here we have the 2016 outcome, okay? So there's two different things that are going on here. Firstly, the difference is probably quite noticeable that these here, I think these are census tracts, where essentially what we're measuring here are actual precincts, so they're a much smaller geographical area, so you get a much more nuanced picture in the outcome that's been selected. And then the second thing I will say is that obviously this isn't some sort of random outcome that you get when you have political elections, for example. And when I say that, what I mean is that the places that are closer together are much more likely to vote in a similar way because of the way that we discussed the modifiable areal unit problem previously. So obviously you're drawing kind of artificial statistical boundaries around a bunch of areas that might have very similar properties, and therefore they're more likely to be kind of similar to each other, right? These aren't independent entities. There's a geographic effect taking place below these statistical areas, which means in rural areas you're much more likely to have similar outcomes, just as you are in urban areas, okay? Because you have free flow of ideas, free movement of people, and therefore you end up with places being relatively similar to each other if they're closer together. So this is actually called Tobler's first law of geography, okay? And that's essentially saying that places that are closer to each other are more likely to be correlated with each other. And this kind of classic phrase that everyone always raises is that Tobler's first law of geography is that everything is related to everything else, but nearer things are far more related than distant things, okay? So this kind of underpins the kind of description that I gave you previously. It's worth checking out Tobler, so I've given you the wiki at the bottom here. I think he finished off his years out at University of California, Santa Barbara, which is a great place to do spatial research. And this kind of gives you an idea of the kind of caliber of their faculty which they've had, because everyone kind of knows this phrase within geography, right? And this doesn't just apply to humans, such as via population density. It's also related to things like elevation, temperature, and other socioeconomic factors correlated with population density, like income. And when I say that things are, highly clustered, this just gives you an example of how this is definitely true. Okay, so this is the population density of the United States, the contiguous United States on the left-hand side here. And actually, this looks quite similar in some ways to the voting maps that we showed previously. But actually, if these were just randomly assigned, you would end up with a map that looks basically just like this over here. So there's no discernible pattern that exists across space. It just looks like, it's random. There's no way to easily interpret this. Whereas obviously here, there are actually very similar patterns. So you have much higher densities along the coasts and much higher densities in areas that aren't mountain ranges, okay? So if you look at where the Rockies spans down, you've got very low populations pretty much all the way across that belt of mountains. Whereas along the coastlines on the west coast and the east coast, you've got very, very highly populated areas. And you can see with the elevation map down here actually that the elevation aspects are also highly clustered, right? So you've got, again, quite low-lying areas along the coastline and the east coast, and also to a certain extent on the west coast. Whereas then that huge area where you don't really have much population is where you've got incredibly high, relatively mountainous areas. Maybe the conditions aren't as good for growing crops traditionally, and a lot of these kind of spatial settlement patterns ultimately have quite strong historical antecedents, okay, antecedents. So essentially maybe, a lot of towns may be there because 100 or 150 years ago, that was the trading post for a bridge across a river, so it's easy for everyone to kind of get to. And then they end up kind of springing into some sort of trajectory where over time they grow, depending on kind of the strength of the economic resources in that area. So some cities will kind of rise and then decline, particularly, for example, if they're in areas where the population is kind of declining as well. Maybe there's not as much work relative to other places which maybe have very strong economies, okay? And this kind of explains that dynamic that we have between, the east and the western parts of the United States, and then maybe the parts in the middle, which, many parts haven't been doing that well, but particularly since the global financial crisis in 2008, and they've had, population loss, and also kind of declining industry, and that's probably only going to increase, particularly in those areas in the middle of the country which has traditionally relied on things like gas and oil as their main part of their economy. Okay, so just to finish this off, this is how the elevation map looks, but this is how it would look if it was completely random. So obviously elevation is also highly clustered. So spatial autocorrelation can be positive, it can be negative, or it can be zero. Okay, so this is basically just saying that you end up having these correlations of patterns that you're looking at across space. So if you have a positive spatial autocorrelation, that means that the things close to you are basically very similar. So if you are one of these grey squares here, all of the ones that are around you are most likely going to be very similar to you, or the same as if you're one of the white squares here, most of the squares around you are going to be very similar. Whereas if you've got the negative spatial correlation, then basically the things that are close to you are actually very different. Okay, and then in the middle, as I explained before, we basically just have kind of random outcomes, so no spatial autocorrelation between these. So that has kind of ramifications for how we understand the problem or how we interpolate data in the future. Okay. There are things that kind of try to plot this distance effect. Okay, so let's say that we want to use a scatter plot to look at how some sort of indicator varies based against distance. Okay, so let's say that this is voting preference on this y-axis here, and let's say that we're going to use this variogram, so therefore we have the distance from a certain point on the x-axis here. Essentially what we end up with is that as we move away from that initial point, we get greater variation in the vote of preference. Okay, so places close together are quite similar in their variance, whereas you start to move further away, you get greater diversions in preferences, for example, whether that's political preferences or whatever. So this variogram approach basically allows us to have these different kind of plotting aspects. Okay, so here we have something called a nugget, which is the uncertainty when the measuring locations are close to each other. Okay, and we have the range as well. So the range here is the distance at which the difference in attribute is no longer correlated. So if we look at the distance here, once we go over 25, let's say this is kilometers, basically there is very little variation anymore. Okay, so that's the point at which there's no kind of correlation between the underlying units that you're measuring. And we also have the CIL, which is basically the variance at which the distance and the attribute are no longer correlated. Okay, so that's again related to the range point that I just emphasized. So you can look at it down here as in terms of an actual empirical application. So imagine that this is distance in meters and this is the community dissimilarity index. Basically, as we get further away from this 0 point, the community increases in its dissimilarity. Okay, so it becomes less similar as you move away from that point at which we're measuring. And then after this, 240 meter point here, this kind of effect vanishes. Okay, so the spatial autocorrelation effect disappears, and then you end up with very little similarity, or at least the effect remains static. Okay, so spatial autocorrelation matters, but we also need to be aware that beyond a certain point, as I just emphasized before, there may be no correlation, okay, after that point. So let's say that we are 200 miles away from a city, and basically we can't then begin to kind of interpolate new data points once we're over that 200 miles because there's increased dissimilarity. Okay, so it kind of goes back to that empirical application I just showed you before. Once you get past the top of the range, so this CIL value here, you end up getting less of a kind of effect where you get this correlation between these different areas, and that's important if we need to do things like try and predict data values. Ultimately though, this kind of spatial autocorrelation causes quite a lot of headaches for people. Okay, so if you're doing implied empirical statistics and you want to create regressions or something like this based on data that could be spatially autocorrelated, then you really need to be aware of this, because it kind of breaks that fundamental assumption that we covered previously where you have independent random samples being collected, because a lot of the samples that you're collecting, if they're spatially autocorrelated, aren't going to be independent. Okay, so just think of it this way: if I told you that we were going to measure reaction times with a ruler, and I was going to tell you each time you had to someone was going to drop the ruler and you had to try and catch it, so we can measure your reaction time from recognizing when the ruler's falling to when you catch it. Each one of those individual data points that we would get on your reaction time would be independent. They do not relate on to the previous experimental run that we carry out. Whereas the issue here is that if we end up with voting preference and we're taking all of those areas from, say, Fairfax County, because there's a lot of spatial autocorrelation because they're close together, and you have these kind of spillovers between these areas, these are artificial boundaries. These are basically not independent samples, okay? So you essentially have to be aware of this, and you might even have to correct for it in your statistical test. Okay, so you can have this spatial autocorrelation issue either being kind of global within your data set, so you can use a single measure of autocorrelation for an entire study area, whether that's Fairfax City, Fairfax County, or the whole of the state of Virginia. Or you could actually have a separate measure for each geographic entity within your data set based on the neighbours which each entity has. So you could look at the local spatial autocorrelation. Now I'm kind of getting on to this thing which we're going to look at over the next few slides called neighbour analysis, and this is interesting because there's lots of different ways that we can kind of look at whether points or polygon areas kind of have neighbours around. So we could classify these in lots of different ways. We could look at adjacency, so we could look at whether polygons actually share a common border with other polygons which have either similar or dissimilar factors, okay, whether that's political voting preference or whether it's socioeconomic factors, things like age, gender, race, this type of thing. Or we could look at other kind of neighbour analysis techniques, so we could look at some sort of distance threshold. So here, this is basically where we look at the distance from one neighbour to another. So whereas before with adjacency, we're very much thinking of these things in terms of polygons because we need kind of joining boundaries. This distance threshold here is essentially could be applied to either of them, okay? So you could use points, you could measure the distance threshold between each of them. If you had polygons, you could actually take the centroid of the polygon and then measure the distance threshold from each one to each other one. And you can also use something called inverse distance weighting, okay? And that's basically where you consider whether entities are actually kind of neighbours, basically as a weighted function of their distance to each other, okay? So nearer objects are more likely to be neighbours. Further objects based on the distance are less likely to be neighbours, okay? So there's these different ways that we're actually able to kind of categorise what we call as neighbourliness here. But essentially this is really important from a spatial statistics perspective because it enables us to actually think about nearest neighbour analysis, these types of techniques which you might have heard of before, might have carried out, but they're a really good way to kind of classify and quantify the relatedness of different factors across space, okay, depending on whatever your research topic is. So I'll give you an example now, and we're going to focus both on nearest neighbour analysis for points, but also quadrat analysis. So, point patterns, as I mentioned before, are basically global in their method. They consider all of the data points within the data set that you're going to assess. We could think about the spacing of the points in terms of, well, how far are each of the points away from each other? This is what we're going to do in nearest neighbour analysis. Or we could think of kind of what the systematic structure of the points is overall, and that would be kind of focusing more on a kind of quadrat analysis, where we would put those points into some sort of quadrat, so rectangular, square kind of grid, and then look at where the points are all distributed, okay? So in both of these cases, we're essentially trying to determine if the pattern has occurred entirely at random, or whether at some sort of significance level we're basically able to say that we think that the process has occurred because of some sort of other significant difference, okay? So we're going to be using the similar sort of testing that we've used in the previous cases, just applied to spatial points here. And ultimately we're going to be looking for those types of p-values that indicate some sort of significance level, for example 95% significance, that the result hasn't just occurred at random, in order to give us some sort of certainty to the conclusions that we take. So one of the ways that random processes are often kind of characterized when we think both spatially and temporally about randomness is via the Poisson distribution. Okay, and we covered Poisson distributions previously when we focused on probability. And one of the ways that I've kind of engaged with this previously in spatial analysis is when you're actually like assessing the usage of a wireless network. Okay, so we've all got cell phones, and I'm pretty much on my cell phone every hour, and you're going to want to look at if you're an addict like I am to Instagram Reels, then basically you're going to want to connect to the network, and you're going to want to actually stream all of that high quality video content like straight down onto your device as soon as possible with no latency, right? So somebody somewhere basically needs to kind of consider, well, how many people are actually going to try and access like high bandwidth video content at once within our cell area, and the way that they generally do that is by using a Poisson distribution. Okay, and they're going to have to say that user Y is going to be accessing X amount of data over this period of time, and user X is going to be kind of measuring, is going to be demanding this kind of data content over time, and basically you can then kind of use these kind of distributional patterns to kind of make estimates as to how much data you think is going to take place across a cell area at different times of the day. Okay, so that's one way in which you can kind of approach this this problem. So let's get into the nearest neighbour analysis now, and obviously you've got McGrew et al., you've got page 211 where you can look at this in more detail, but essentially what we want to do is just to kind of determine if the point patterns that we've obtained here empirically are actually just kind of a random process, or whether there's something significantly different that's going on. So in order to kind of meet these requirements for this test, we need to have points which have been randomly sampled, and then we also need to have sample points which are independently selected. So that's important. These can't be correlated in any way. And essentially then we'll have a set of hypotheses, and these are going to be, in the null hypothesis case, that essentially the mean nearest neighbour distance is going to be equal to the nearest neighbour distance here that was based on the random mean. Okay, so we've got the observed mean here, this NND bar, and we've got the random mean here, which is the nearest neighbour distance based on just kind of a random outcome process. Okay, and in the null hypothesis they would basically just be the same. Okay, so this is exactly as we kind of approached these hypotheses in other tests, so there would be no difference between what we've observed and what we would expect. Whereas in the alternative hypothesis, we would basically say, if it was two-tailed, we would say that they're significantly different, but we're not actually saying whether it's larger or smaller. We're just saying they're different. We don't know which way. Maybe this is the first time that we've assessed this problem, so we're not able to make a directional hypothesis. You could always make a directional hypothesis. So here we have an alternative hypothesis where the observed value is larger than the random mean that we've got, or you could do vice versa. The case that the observed mean is actually smaller than the kind of random mean that we've obtained. And essentially when we've got that information, so there's the random mean metric and the observed mean metric, we can subtract one from the other and divide it by the standard error of the mean for the nearest neighbour distance, and we get this ZN test statistic here, which then we're able to obtain a p-value for, in order to assess if we think that the results have just occurred by chance or not, or whether there's some sort of other significant effect that's taken place. So what we're basically doing here is, this is kind of analogous to how we compared observed frequency distributions in the previous classes against perfectly normal frequency distributions. So we want to determine the nearest neighbour distance for each of the points within our data set using Euclidean distance. Okay, so the straight line distance between each of those points, and we've worked out how to take these types of measurements previously. We need to get the observed mean, which is this NND bar metric here, so therefore we need to take the sum of all of the distances from all of the points, and then we need to divide it by the number of points that we've got in the sample, and it's going to give us this mean distance, and it's going to be an absolute measure in the original units that we measured the points within. We then need to get the mean nearest neighbour distance for a random pattern. So this is basically just saying for the area that we are assessing, for the number of points that we've got, find me the mean distance if those points were just randomly occurring, okay? And essentially this is basically quite similar to, imagine that this is just the mean distance between all those points, and that would actually look, as I'm going to show you shortly, quite like a hexagon area, okay? And I'll show you that in a future graphic. So once we've got that, so these are the two numerator metrics as I showed you in the previous case here. We then need to get this standard error of the mean denominator. Essentially we need to basically take 2.26136 and divide it by the square root of n multiplied by n divided by the area, okay? So this gives us that standard error of the nearest neighbour distance. So it's this sigma nnd bar. So the mean nearest neighbour distance is in absolute terms. So if this was in meters that we measured all of the points in, then our mean nearest neighbour distance would also be in points, right? So this isn't kind of relative. It's not going to give you some sort of understanding of the overall distribution in kind of relative terms. So essentially, to do that, what we need to do is we need to basically get a standardized index for the nearest neighbor distances, okay? And it's actually really easy to get, because all we need to do is take that observed nearest neighbor distance and divide it by the nearest neighbor distance that randomly occurred, okay, the mean distance. And if you get this R value and it's 0, then you've got perfectly clustered data. And then if you've got 2.149, then you've got perfectly dispersed data. With a value of 1 being approximately random, okay? So we can think of this as a descriptive spatial statistic approach to understanding the level of kind of dispersion of these points across an area which we're measuring. So this is basically what it would look like if we had R equals to 0.5, so these are actually highly clustered. 1.25, so this is only slightly more dispersed than the random outcome here. And then here for this this value of 2.1491, this is basically perfectly dispersed. And they look like triangles, but they're also hexagons if you look within them. This forms a hexagon shape, and the way that this is calculated here, if you're into your geometry, is basically trying to find the mean distance between each of these points within this kind of hexagon shape, okay? So I have a little bit of research experience in using these kind of shapes to kind of divide up different areas and then actually do things that you want to do within them, whether that's like design a network or actually assess the demand usage from different times of day for people within those boundaries that you've artificially placed over them, okay? So area is important, obviously, because here what we're doing is we're considering the boundary and then the density of the points within them, and that means that basically we're going to end up with some of those spatial statistical issues that we've covered within the previous lectures, okay? So it's really about the boundary delineation. So how does this affect the density of the points and the result that you actually obtain? So you need to kind of be aware of this, and you need to make sure that you're using a polygon boundary area that's kind of coherent with the spatial process that you're trying to assess. So obviously, if you're interested in comparing cities and the density of, let's just say, people or vehicles within city areas, it would be incorrect to then start to compare Richmond and Virginia City by using the county boundaries, right? Because you have all of this outside boundary space that basically skews your results, and they don't make them directly comparable. You would really want to use the city boundary because that would best encapsulate the kind of urban areas that you have. So you need to be aware of kind of the boundaries that you're using for this nearest neighbour analysis part. So we can also look at quadrat approaches. So that's basically where we're putting these tile grids across the study area and then looking at how many points occur in each of those tile grids. So you can look at this on page 216 in McGrew et al. But basically here we can determine if the point pattern is actually just a random process, or if we're actually got really a significantly different kind of process taking place across here. Okay, so if we have a random sample of points, then we're able to also, for the requirements for the test, we have to have a random sample of points, and we also have to have those independently selected points as well. So there can't be any dependence or correlation between those existing points that you've got in your data set. For the hypothesis here, we basically are saying that in the null hypothesis case, the variance mean ratio, this VMR value, is equal to 1. Whereas the alternative hypothesis would be that the variance mean ratio is not equal to 1. Okay, so we'll go into the VMR very shortly. You can also have directional hypotheses, basically saying whether you think that the data set is more clustered or more dispersed based on some sort of a priori knowledge which you might have. And then essentially we can take this variance mean ratio and multiply it by essentially the number of degrees of freedom in the data set, and it provides us with this chi-squared test statistic. So Quadrat Analysis focuses on how often those points occur in frequency terms within each one of those tiles, and I apologise that this isn't quite as high resolution as I normally like to have in my slides, but it gives you a flavour of what's written in the book. So your quadrat is just like a tiled shape, okay, and now I would just create this automatically within my code, and I could just put it onto an area of points and do it all manually. But during my undergraduate, my lecturers were teaching me basically how they used to do it in like the 80s, before you could easily do this stuff within computers, and they would have like a metal kind of square, and they would have like these lines within it, and you basically, I did this experiment where we went to this ecosystem area, and we would like throw the quadrat, and then when the quadrat landed randomly, you would go into the quadrat and you would count all the different species of plants or heathers or insects that were basically within each one of the quadrats, and you would do hundreds or thousands of times to develop a sample understanding of an ecosystem. Okay, so it's much easier for you to kind of do these days, rather than just having to go out and manually collect all of this this data by hand, essentially. So this is what you would end up with if there was no variance. You would have this kind of perfectly dispersed set of data, these points within these tiles. Highly clustered, you would end up with large variance, and the points would all be kind of huddled together in different patterns. Or you could end up with moderate variance like this, where you'd have some clusters and some dispersion. Okay, this is more kind of random down here. So that VMR that I covered just very quickly is basically it's used to standardize the variability in the cell frequencies relative to the mean frequency. Okay, so we can get this VMR value by basically dividing the variance of the cell frequencies by the mean cell frequency. Okay, so we can get the mean cell frequency, this denominator here, by just taking the n value, which is the number of points, and dividing it by the m value, which is the number of cells. So that's very easy for us to get our denominator value. But then for this VAR, this variance of cell frequencies valued, the numerator, we actually have to do a bit more math. So to get this, we basically have to take the sum of f multiplied by x squared, and then we need to subtract it from, and then we need to get the numerator here, which is the sum of f multiplied by x, and then we need to square it afterwards and divide it by m, and that should give us the top part. And then basically down here we take the number of degrees of freedom, so it's the number of cells minus 1. And that should yield basically the metrics that we need to get this VMR outcome. So don't worry about a lot of this math in the actual lab this week and in the homework. I'm pretty sure most of it is all actually going to be within ArcMap, so I think you're just going to need to work out how to do some of those calculations in the GUI. So basically the number of degrees of freedom that the chi-squared has is n-1. Okay, I think we've covered that already. Obviously the boundaries that you put around those data points are going to have an impact on the values that you obtain. So this means that you need to kind of be aware of the quadrat size. So this could yield basically the same set of frequency outcomes, whether you have this kind of clustered data here or this quite dispersed data over here. And they're going to yield the same values, so you need to be aware of those modifiable aerial unit kind of problem issues depending on how big your quadrat sizes are. Okay, so really what you want to do is kind of make it big enough to fit around the visible cluster of points. And to do that, you might want to have at least twice the average area per point, okay? So, these are just some general rules which you can follow. Let's move on. Let's get on to the area pattern analysis, okay? So, previously we were focusing just on points. Now we're going to focus on polygons, and we're going to focus on join counts, and then we're going to look at some of Moran's eye, some calculations using Moran's eye. So the area pattern analysis, essentially this is very similar to what we did with points. We're just focusing now on those kind of polygon boundaries, which is kind of useful because actually a lot of the data that you might get and then start to categorize or gradient might be in census tracts or zip codes or states or counties. So essentially you need to be able to investigate using some spatial statistical techniques, whether that's join count analysis or Moran's eye, as we're going to cover here. So you can look at this in page 223 in McGrew et al. And that might give you a little bit of background as to how we calculate the test statistic here, which is this ZB factor. And the objective of this is basically to determine if the process has just occurred at random or whether there is some sort of other significant effect taking place on the kind of distribution of the categories which are being assessed within those polygon areas. So that what we require here is that each area is assigned to one of two categories, so this is binary, and what we want is a consistent methodology of determining adjacent and non-adjacent pairs of areas, okay? So we can think of this as, let's say that we're going to keep that kind of standard example I give you, which is house prices in Fairfax City, and I'm going to say to you, I'd like you to go out and to get the house prices for those areas, and let's say we get the kind of boundary parcel for each land, for each house, sorry, with the land around it. And then I want to categorize it into whether that house is actually worth more or less than $500,000, okay? And you get a binary outcome. So if it's worth more, let's say we allocate it 1. If it's worth less, let's allocate it 0. And this would then allow us to do this type of join count analysis. We'd look at how the polygons are all kind of joined to the other ones, okay? In the null case, we would say that the OB value, which is the observed number of joins, is actually equal to the expected number of joins that we have, okay? And then in the alternative hypothesis, we would basically say that they're different, okay? So the observed number of joins that we get does not equal the expected number of joins that we would think that we would get if it was just kind of the outcome of a random process. And you could also use directional hypotheses, whether you think that the observed values are higher than the expected amount, that's where basically you would have more dispersion, or you could basically expect that you would have fewer observed joins in the polygon areas than the expected amount, and therefore you would basically end up with more clustered data, which I suspect if we actually went out and did the house price example, that's probably what we would end up getting. So this ZB factor here is basically the expected number of joins minus the observed joins, okay? And we divide by the standard error of the joins. Now traditionally this was basically done just using like a chessboard as an example. So you would end up with black areas and white areas, and you would just look at how many areas would then fit into will basically be adjoining those other areas, okay? So obviously if it's a chessboard, then you would have the most dispersed outcome, but then you could look at this also for polygon areas like house prices, and you would end up with probably quite a clustered difference. So the join count analysis, this is basically where you have a shared border or edge that we consider a join. We're not talking about spatial joins here in GIS, and that aerial data is then put into some sort of binomial outcome, so it's either true or false, or whatever, black or white, or whatever you want it to be. So I'm just using black or white here because that's kind of the traditional terms that are used for these different areas based on a kind of chessboard approach. So essentially you can then count how many areas which are black and joined together, or white and joined together, or whether they're black and white joins which match together. And basically you end up with similar joins or dissimilar joins, and then you can kind of use this data to actually crunch the numbers that we're interested in, okay? So we're focusing on how many are similar and how many are dissimilar. We can do this in multiple different ways. So how do we actually obtain that sample data? Okay, we're going to go out and we're going to just do free sampling. Are we going to basically just randomly sample different areas and see what we end up with? Or are we going to use some sort of non-free sample? Okay, so we're going to confine this to a study area like Fairfax City or Richmond City or Alexandria or whatever. Geographically, non-free sampling methods are more pervasive, right? Because people often do kind of area studies or regional studies, and they say they want to kind of specifically focus on the dynamics in one or two areas and kind of compare them. So the observed join count here is OB, the count number, and the expected join count is this EB value. Okay, and to get the EB value, what we're doing is we're basically saying we need 2 multiplied by J, which is the number of total joins, multiplied by the number of black joins, number of white joins to get the numerator, and then we divide by the number of samples that we've got, so the total number of areas multiplied by the number of degrees of freedom for the total number of areas. So that's how we get this EB value. And then we've got this long equation here for us to actually get the standard error of the joins. Okay, so I know that you probably aren't going to like this, but we just need to crunch through it quickly. And if you just think about breaking it up and kind of placing those numbers in a kind of manual way into little parts, it's a little bit like when you have a really big word when you're younger and you need to pronounce each syllable and then stick it all together. Okay, so we need to take the square root of this EB value, the expected number of joins, plus, and then here we need to take the sum of L is the number of links multiplied by the number of degrees of freedom for the links, multiplied by the B, then multiplied by the W value, and that gets us our numerator, divided by the total number of areas multiplied by the number of degrees of freedom for the areas. And then I'm not going to go through this persistently, but you then need to plug those numbers into this next part of the equation, then subtract the EB value squared, okay? And we can do that now. So this is the kind of simplest way that I could possibly present it. So I apologize if you kind of see this and you're like, ah, because it's scary. But basically, look, this is just 6 polygons, okay? So here, all we've got are 6 very simple polygons. We've got 7 joins, okay? So 1, 2, 3, 4, 5, 6, 7. 4 of these are green or black, which way you want to think about it, and 2 of these are white, okay? And essentially, that means we've got a J value of 7, a B value of 4, a W value of 2, and the total number of areas we've got is 6. We can take the sum of the number of links multiplied by the number of degrees of freedom for the links, and that gives us 20. So we're able to kind of extract that part out of the kind of more complicated equation. We can take the observed number of joins, which is going to be 4, okay? So that's and then we also need to get the expected number of joins, okay? So this is the 2 times J times B times W divided by N multiplied by the number of degrees of freedom, okay? So that's basically what we've ended up here. 2 times 7 times 4 times 2 divided by 6 times 5 equals 3.73, okay? So this kind of gives us all the nuts and bolts that we need then in order to start to calculate this. We do need to get the standard error of the joins, okay, and we need to plug those numbers into here. So we've got this EB value here that we calculated, 3.73. We've got most of the components, we've got all of them now to carry out these 2 parts of the equation, and then at the end we can again plug in that EBW value squared. So we end up with these, so we're basically taking the square root of 3.73 plus 160 divided by 30 plus 2,112 divided by 360 minus 13.94, and we get, rather surprisingly and quite simply, a standard error of the joins of 1, which makes it super easy for us then to calculate further because there's no kind of decimalization we need to worry about. So we have this z value that we want to get down here in the bottom corner, and essentially we need to take the observed number of counts and subtract the expected number of joins, and then divide by that standard error value that we obtained. So it's 4 minus 3.73 divided by 1, which is 0.27. And if you then look at the p-value for that 0.27z that you get a p-value of 0.4. and as a consequence that's not below the kind of 0.05 level that we would be looking at in order to be 95% certain that this outcome is significantly different from just a random occurrence, okay? And as a consequence we fail to reject the null hypothesis, that means that this outcome essentially it looks like it's occurred by random. We don't have strong enough evidence to kind of conclude otherwise. Great. Let's just finish off now. I promise you we're on the home straight for this course, for this lecture today. And essentially we're going to think about Moran's eye. Okay, so this is a thing which allows us to look at the level of spatial autocorrelation either globally or locally within our data set. Okay, so the objective here is to identify non-random spatial patterns, so some sort of degree of autocorrelation within our data points. We would basically expect to have at least 30 geographic features, and those features could be ordinal, interval or ratio attributes, but they can't be categorical, okay? So we're expecting some sort of numerical, even if it's ordered, some sort of numerical information to input into this. The hypothesis in the null case is that essentially the process we're looking at is just randomly distributed, so there's no correlation between those points or areas that we're using to assess here, whereas the alternative hypothesis is that the attribute values are basically not randomly distributed, okay? So we have a test statistic I, and that's what we want to obtain, and what we're basically doing here is, so rather than show you just the math and talk you through it, I've kind of broken it down here. So we take the number of areas, which is n, and then basically what we're doing in the next part here is we're basically getting the sum of the cross products for all of the contiguous pairs I and j, and you'll remember that this looks quite similar to what we've done before. So we're subtracting the mean value of x from each one of the xi or xj data points that we've got, and then basically we multiply them and sum them, so you get the sum of the cross products. And then as the denominator here, what we're basically getting is this j, which is the number of joins multiplied by, and then this is the variance of the area attribute, okay? So the sum of the mean subtracted from x squared. So for Moran's eye, basically what we end up with is a set of, we get this I metric, okay, and that's representing the level of kind of dispersion, randomness or clustering within the underlying data, okay? So if I is below 0, then basically the data are dispersed. If I is equal to 0, then basically the data are kind of randomly distributed, there's no relationship. Whereas if I is larger than 0, then that basically means the data points are highly clustered, okay? And we can use this on both points and areas, okay? Basically, -1 is perfect clustering of dissimilar values. 0 is no autocorrelation, so kind of perfectly random outcomes. And +1 is perfect clustering of similar values, okay? So Moran's eye ranges from -1 to 1, as you've already noticed. So just how different is 0 from I? Well, we need to convert that to a z-score, okay? So we get the I, and we have to subtract the expected value here, which is -1 divided by the number of degrees of freedom for the data set. When we subtract that EI from the I that we've got for our numerator, we can then divide by the square root of this var I, okay? And we're not going to calculate that here because that's really complicated. So we're going to basically do that within ArcGIS and let the kind of computer do the heavy lifting for us, okay? So we can also calculate Moran's eye at the local level, so we can use it to calculate an autocorrelation score for an individual, whether that's an object, an entity, a person, an area, whatever, and then we can use it to find kind of hotspots of autocorrelation. Okay, so let's see the output. So this is kind of the classic example looking at residential segregation within the United States. Obviously within GGS there are faculty members who particularly are experts in quantitatively assessing community segregation and things like this through this type of data. And here what we're basically looking at is in Detroit, and this is basically the racial composition of these statistical areas, okay? So here this is the percentage of white people in a particular area, and you can think of it in terms of racial heterogeneity. So if it's under 20%, then these areas are most likely extremely racially heterogeneous. And then if this percentage metric is over 80%, then you can think of this as basically extremely racially homogeneous. Okay, so we can then kind of assess these different areas based on these kind of racial compositions, which provides us with very interesting understanding as to the kind of distribution of people living in these areas. Okay. So we can see the map on the left-hand side. We can see already that it looks highly segregated, right? So this is Detroit, the city. You can see because the statistical boundaries have got much smaller, which means if you know how these are designed, then basically you have higher population densities in those areas where the boundaries are smaller, because they usually like to have kind of maximum number of people in each area. So where you have high population densities, you end up drawing lots of boundaries. And over here you probably have very low population densities, which these are probably very rural areas, because you have quite large boundaries, which means probably not got many people living here. It's probably very rural Michigan farmland. Okay, and actually if we carry out a spatial autocorrelation test, so we'll get Moran's I for this data that we've got here based on these ordinal categories. Essentially we get a Moran's index of 0.88, so it's highly positively correlated. We get a z-score which is huge, it's like 48.26, and that corresponds to a p-value which is basically like 0.00000000, so very far beneath that 0.05 significance level that we would be looking at. So this is saying that we have highly autocorrelated data. It's highly unlikely that this has occurred by random, and then there's clearly some other types of spatial processes which are going on there, which are affecting the distribution of individuals living across these different areas. Okay. We can also use Moran's I as a consequence with this data to then start to try to understand how clusters kind of occur, where they sit within the distribution based on this kind of autocorrelation approach that we're using. Okay, so Moran's I allows us to classify areas into 4 different categories, and they correspond to the locations of the points in the 4 quadrants of the plot. So these categories are high areas, low high, and high low relative to the mean. Okay, so if we have high over here, this means that they're above average and correlated. If they're low down here, this means that they're below average and positively correlated. And then if we have low high or high low, then these are basically outlier areas. Okay, so what we end up getting is, so over here we've got the high clusters in these black colors here, which means that they're highly autocorrelated. And we have the low cluster here. Oh, and these are above the mean as well in terms of their racial composition, or lack of it, as I may say. And then down here we have these blue areas, which so we have these are areas that are low in the distribution but also highly clustered. And then basically we have all of these grey areas in the center here which aren't significant at all. Okay, so it's really these these areas labeled black in the north, and then these areas labeled blue here, which are kind of significantly different from what we would expect. And basically these are where you have very high levels of spatial autocorrelation, okay, between the different entities. So among the blue areas and among the areas labeled black. Okay, perfect. Well, I don't want to take any more of your time. I hope that you kind of found some of that content interesting today. This is kind of a fun class to teach because some of the other spatial statistics content is kind of more kind of basic statistics, and it doesn't really get into the spatial processing aspects, whereas a lot of the stuff that we've kind of covered today is very kind of specific to spatial statistics. And therefore if any of you have done kind of basic statistics courses before, I assume that some of it will have been quite new to you. Okay, so I'm going to wrap it up here. I'll see you in the next sessions, and let me know if you've got any further questions about the content that I presented today. So thank you very much for your time, and I'll see you all again soon. Take care. Bye-bye.